So we can start this edition of the COMSOC video seminar. I am very happy that we have two excellent speakers today, and we will hear probably two excellent talks by them. The first is by Thanh Nguyen from Purdue, and he will talk about stable social choice. And then the second by Andrei Constantinescu. We have the usual format, 20 minutes talk, 10 minutes discussion, then 10 minutes break, coffee break in between. So that's the usual format. So Tan, please, the floor is yours. Please share your screen and you can start.
Thank you. So time is short. Let me just go right away to the notation. So this is standard notations. I have a M finite set of alternatives, and I denoted the capital A. And I have a set of voters, N voters, and each voter has a weak preferences over the alternatives. And I want to select either a deterministic alternative or a lottery over this alternative, right? Probably. So this is very much standard notions from social choice theory. And the main goal of this literature is to select an outcome that fairly represents the aggregate preference of individual, right? Whatever that means. So over the last 50 years, of course, the field has focused on formalizing this objective using various axioms, and often showing that certain collections of axioms are either incompatible with one another or identify selection rule and that satisfy this set of options, right? So in recent years, a lot of you in the audience are kind of, especially in the context of multi-winner setting, think about notions of stability conditions as conditions to capture these fairly representations of social choice. So in English, it's kind of mean that a sufficiently large group of voters should not be able to find a sufficiently better alternative. So the ideas when I start writing this paper is really want to use this idea to in the context of a single winner social choice, a standard framework. And so actually this notion is not that new, right? It traces back all the way to Nicolas de Condorcet, right? So here you can think about the Condorcet product is that the sufficient large is the majority, and the sufficient better is just a better, right? So it say that there's instances of voting when it's impossible to select a deterministic outcome that has the support of majority, and it's of course is a well-known example of 3 voters and 3 alternatives. So now one might ask, if I want to change this notions of sufficiency large to not from majority to any, say, constant fractions of voter, can we have a deterministic outcome that satisfy it? So the answer is again, no. You can extend this example that such that no deterministic choice can have support for any epsilon fractions of voter, right? So now it's natural to ask that, oh, okay, so maybe it's because we really try to select a deterministic outcome. What if we allow randomization? Can randomization help in this context? The answer is literature also said no. Condorcet winning lottery does not exist even when we change the way we define the preference over the lottery, right? So Richard Steckhauser has the first papers, right, saying that instead of thinking about deterministic outcome, I'm thinking about a preference over the lotteries based on expected utility, then Condorcet paradox still persists. Harris this show that now if I change this to stochastic dominance order, that still doesn't solve the problem, right? So there's a recent notion called pairwise comparisons ranking over the lotteries, and there's a, we know this is a well-known maximal lotteries that kind of satisfy the support of majority, but in fact, this lottery is also not that kind of stable. It's not only supported by majority in expectation. Okay? So seems like randomization doesn't really help us to solve the Condorcet paradox. So in these papers, I want to change that opinion. I really want to show you that actually it does, right? But we have to do it a little bit carefully. If we restrict the kind of the deviations to deterministic alternative only, and we have to define the comparisons between the lotteries and the deterministic alternative carefully, then randomizations can help in three ways. It helped to provide an ex-ante fairness notions of probabilistic social choice. It also allows us to provide a justification for ex post implementations of the lotteries. And third, it's going to reveal the precise trade-off between how big group size is and the degree of improvement that we need in social choice. Okay, so that is kind of the punchline of the paper. And I have 20 minutes. I'm not going to cover all this, but first I'm going to define what it means to be a stable lottery. And I want to quickly show you that you can try to define a little bit of stronger definitions, but it's often just leads to impossibility. And I'm going to show you that all existing mechanism does not satisfy this notion of stability. And I show you a constructions that satisfy that. Okay. Okay. So here's definitions. So I'm give you a deterministic alternative A and a lottery in delta sub A. I say that A strictly preferred to P and denote by this. If I sum up all the probability of alternative that is strictly worse than A, that summation has to be at least 1/2. Okay? So it means that if I play A against this lottery, the probability that A wins the lottery is going to be at least 1/2. Okay? I call A weakly preferred to P if the probability that either A draw or A wins the lottery is at least 1/2. Right? And a lottery is ex-ante stable if for any choice, any alternative, deterministic one, that is better, strictly better than the lotteries, then the number of people that satisfy those criteria have to be less than the majority. And a lottery is ex post stable if for any alternative in the support of the lottery, the number of voters that prefer A, weakly prefer A to the lotteries have to be at least the majority. Okay, a little bit kind of take a little bit time to digest. So it means that the lotteries, I really want the lottery to have satisfied both of these property because it's nice, right? So probabilistic choice, really thinking about it, has two steps to it. The ex-ante step is that when voter agrees on a common lotteries, and we can think in this case, the lottery as a promise to voter, right? So ex-ante stable mean that when all these voters come up with a promise, with a plan of the probabilistic, no majority can find a better deterministic outcome. Yeah, and the ex post stability say that, okay, so when I realize these lotteries to any realizations, no majority regret it, right? Because we are giving them a promise, this lottery, and any realizations is actually weakly preferred to the lottery itself by at least half of the voters. Okay? So now you can think about why did I come up with these definitions of strictly and weakly preferred. So you can think about other type of preference. For example, this is based on expected utility or based on pairwise comparisons. So if here's I focus on pairwise comparisons. that restrict myself to comparing a deterministic alternative with a lottery. So it's called PC1 in the literature. So it boils down really to say that the probability that A strictly wins a lottery plus half the probability that A draw with a lottery is at least half. So obviously you can see that, strong preference in my definition is going to imply PC1, and PC1 going to imply the weak preference. So however, if we insist on these comparisons, then there will be no ex-ante stable lotteries. And actually it holds a little bit more, even more general, that for any comparisons where you can extend it to a complete preference over the lotteries, and it satisfies a technical monotonicity and continuity conditions, then there's instance of voting when ex-ante stable lottery need not exist. So the implication is that either PC1 or expected utility preference, you cannot guarantee the existence of ex-ante stable lottery. Okay. Now you can also try to replace this 1/2 by a different number, say 1/2 minus epsilon. So in this case, ex-ante stable lottery need not exist either. Okay. All right. So next, I want to show you that the existing mechanisms are not stable. So it's including random dictatorship, Borda max, Borda pro, maximal lotteries. So I don't think I will have enough time to go through each one of them. Let me focus on this maximal lottery. So maximal lotteries, all of you probably know. So it is a lottery that constructed by a zero-sum symmetric 2% game. When I write out the matrix M as a number of voters, like an alternative X more than Y minus the number of voters like Y more than X, and I solve this 2% sum game, and I got the lotteries. Okay, so here's an example. So I assume 3 types of voters. 20% have the first preference, 35, 45 have the second and the third type of preference. Here is where I write out the M matrix. And if you calculate it down, the maximal lottery is going to put 10% on A, 60% on B, and 30% on C. So this is not an ex-ante stable, because if you look at this lottery, 65% of the populations actually prefer A to this lottery. And it's also not ex-post stable because C is weakly preferred to P by only 45%. Okay. So actually, you can construct a stable in this case that put a little bit higher probability on A, a little bit higher on C, and much lower on B. Okay, so here's some other numerical example. You can vary alpha, beta. The maximal lottery is a lot of the time is not stable. Why? Correspondingly, you can construct something that is both ex-ante and ex-post stable. Okay, so the theorem saying that given any instance of social choice, there's always exists a lottery that is both ex-ante and ex-post stable. And furthermore, we can also construct a lottery that is stochastically dominant, efficient, and it's compatible with Condorcet winner criteria. So here's the constructions. So this is a general framework of how I construct, I call it endogenous Borda lottery. So I'm going to pick a scoring function F. It's going to be a strictly monotone, continuous functions between 0 and 1. And for every agent, I'm going to take a lottery. Lottery is fixed, and I'm going to sort these lotteries from 0 to 1 as tracking the intervals, where each interval corresponds to an alternative, and the length of this interval is exactly the probability of this alternative. Okay. And now I'm going to give each alternative, the alternative J, a score. This is an individual score that depends on 2 things, depending on the function itself and also the lottery. Okay? So basically, I look at the interval that correspond to that alternative. I take the average of the f functions inside that interval. Okay, so you take the integral of that functions and you divide by the length of p, and that would be a score, individual score that agent I give to alternative j. Yeah. So the endogenous Borda lottery is such that the lottery is kind of consistent. So it means that the lottery itself is going to give individual score, and also the lottery has to satisfy the endogenous conditions that every support of the lotteries have to satisfy that the total score is maximized. Okay. By fixed point arguments, there always, if the f is continuous, there always exists a lotteries that consistent with both the voter's individual score and the centralized agent who's picking the lottery over the alternative with maximum total score. Okay, I don't know if it's clear enough, but maybe you can ask me a little bit later. So if you choose these f functions to be the identical functions, that's going to correspond to exactly to the maximal lottery. And this is not going to be stable. So we need to choose a different functions. And it turns out if you choose a function like this, g epsilon, and you take an epsilon going to 0, it means that this red function is going to approach to a step function. So going to be kind of 0 until 1/2, and then 1/2 and beyond 1/2 up to 1. Okay, so if you take a g epsilon function, you take a endogenous lottery and you take epsilon to 0, take the limit of it, it's going to be a limit, I call it limit equilibrium lotteries, and it's quite easy to see that this lottery is going to satisfy both ex-ante stable and ex-post stable, right? So simply because say if you want to show that this ex-ante stability, if the voter A like A more than this lottery, then in the scoring rule, the A have to sitting in the interval between 1/2 and 1. So therefore, the scoring has to be at least 1 minus epsilon. Okay, and by the way, I choose this functions especially so that everybody, the average score of the alternative from every voters is exactly the iterations of that functions. And in this case, it's actually 1/2. So there cannot be more than n divided by 2 voters that like A more than P. Okay, so similar, you can see that why that this lottery is going to satisfy ex-post stability as well. Cool. So the theorem number 2, that this lottery is actually is also stochastic dominance efficiently. So the proof is so if you choose f function strictly increasing, then it's very easy to see. But for the function that is kind of in the limits, it has to have a little bit more care to it to show that why such a lottery is efficient. So I'm not going to go into detail of this proof. But I want to here another point that is the trade-off between the sufficient large group and sufficient better alternatives, right? So the idea is that right, we want to capture something that small groups should require substantially improved choices, whether for the large group to deviate a small improvement is good enough. So in order to do so, I'm going to generalize this 1/2 to any personalized threshold alpha. So voter I's strictly prefer A to P if the same probability that A wins the lottery is at least alpha I, and weakly prefer is win or draws with the lottery is at least alpha I. So the bigger alpha is, it means that we require a bigger improvement from the lotteries for that agents to try to deviate. So lotteries in this case is ex-ante stable if is summations of 1 divided by 1 minus alpha is less than n. We can see that alpha equal to 1/2 is exactly the the majority conditions, and similar for the ex-post stables. So theorem saying that there always exists a lottery that is both ex-ante and ex-post stable with respect to any alpha vector. And the proof is kind of very similar. So instead of choosing these functions, you have to choose a function that is, picking at the alpha I instead of picking at 1/2. Okay, just let's give you some examples, some implications of this. So if I choose alpha as is 0.3, it means that you don't need a lot to deviate. Then the group size has to be, at least 70%. When alpha is big, it's only need a smaller group size in order to deviate if they can find such a alternative. And one interesting case is if I choose alpha really big, bigger than 1 minus n, then it means that every single voter should be able to deviate if they can find a better alternative. It means that in stable lottery, every voter receives a top choice with probabilities 1 divided by n. Some people in the audience might think, oh, I know one such mechanism. That mechanism is actually random zero dictatorship, right? So if I choose, everybody has a 1 divided by n chance to choose the best option. So that should be satisfy this property. But the advantage of our mechanism is that it's actually efficient, while random zero dictatorship is not. Okay, so I think I'm kind of running out of time. His conclusion. So Zach Hauser QG paper has a very nice poetry that for preference with one pick, there will be a choice unique that gets truly majority, other choice made with certainty, with lotteries from which to choose. This unique choice wins, sometimes lose. This phrase once again, alas, the nasty psychic choice morass. No man or group should like to see such like a transitivity. We can avoid this dreaded curse with voters mostly risk-averse. So my attempt is really trying to imitate him, and with the help of ChatGPT, here's my conclusions of the paper. For full domain, no rule can stand, no stable choice, no guiding hand. Pure or random or win slide, as voters will diverge and guide. Yet if we frame the choice as right, comparing lots to pure insight, a hidden structures come to light. Two states support, both firm and tie. Ex-ante hope, exposed consent, a charitable in its ascent. Though full domain still show despair, with scope compares, stability is there. Right, thank you. And I think I'm ready to take questions.
Okay, so thank you very much. That was a wonderful end.
Yeah.
And I'm opening the discussion. Well, Nizark has a question. Does this notion easily extend to choosing a lottery over committees? And if so, how does it compare to stable lotteries?
It can, but we're going to lose some kind of constant factor. It's not as tight as the result that I show you.
Okay.
And how does it compare to the stable lotteries from the Cheng et al., Kamesh Munagala et al.?
It's different. So because the Kamesh is still kind of look like the maximal lotteries,
Right.
weighted average. So it's not just counting number of people.
Thank you.
I have a small question just for understanding. Under what conditions are your stable lotteries deterministic outcomes? Do you have a general result about that?
So there's one instance that I know that is when the Condorcet winner exists, then the lottery is returned the Condorcet winner itself.
And only then?
Not only that, but
okay. So there are more cases in which you have deterministic outcomes than just when you have Condorcet winners, right?
Right, yep.
Can you say something about these cases?
No, I haven't thought very carefully about it.
Okay. All right. So Felix has a question. Felix.
Yeah, hi. Thanks for the presentation. So I think it's really an interesting approach. So regarding your definition of stability, I have a question. So you use 1/2 in two different ways. So 1/2 of the electorate, which is fine with me, and you also use 1/2 as a threshold for the sum of probabilities.
Right.
And to me, this seems a bit unnatural because it's, for example, like if you have a person who prefers A to B, and you have a lottery that puts 2/3 on A and 1/3 on B, then A is not preferred to this lottery according to your strict preference relation, right? Because so the problem is you're comparing A and P to each other, but the lottery P may put positive probability on A itself. So therefore, what you mentioned, so you mentioned this PC1 extension, which just says that P should be preferred to A if it puts more probability on alternatives that are better than A than the other way around, which it doesn't use a fixed threshold, seems more natural to me. But it seems like then you don't get existence of your stable lotteries. But
right, exactly, right. So as I show you, there's a relationship between PC1 and weak and strong preference. So PC1 actually sandwich between the two. And it is relaxing that we just have non-existence. So this is the way that
right. But like for you had this the simple example of a 3-cycle where you said that where you had a, I guess, unique stable lottery. I'm not sure. So you mentioned one stable lottery in that example. Is it the unique one?
Yeah, that's a unique one. Yeah.
Because in that example, if you could go back to the slide if you want to, but so the voters in the first and the last column, I think they would actually prefer the alternative A to the lottery. So this, because at least if you change the definition of the extension for comparing lotteries to alternatives, so it's I think this is also an example where you see that this threshold of 1/2 seems a bit unnatural.
This one, right?
Yes, exactly. So the lottery which was stable is the one that you give here. And I think the voters in the first and the third column, they would actually, so the alternative A, so the lottery that you give here is actually less preferred to the alternative A, at least to the PC1 extension, which you mentioned earlier.
So it's in this case, yeah, it's
right. So let's look at the ones in the first column, for example, right? So they, so if they compare A to this lottery,
yes,
so then they should probably intuitively prefer A because this lottery puts more alternative on C than it puts on A, right?
Yeah, yeah. So it actually does for the first voters, A, B, C, actually they prefer A to this lottery, right? Because this sum of these two probability is bigger than half.
But also the ones in the third column, right? I would argue because
well, yeah, so it just the definition.
Because more probability is put on B than on C, and those people prefer C to B.
Right.
So the problem is that there's some positive probability on A there with which you are comparing, but it's again making the same point why I would argue that the PC1 extension is more natural here than having this fixed threshold of 1/2.
Right. Yeah, but so again, so if we extend it to PC1 or other kind of notion that may be more reasonable, then we don't have existence. So
I understand, yeah. But so since we are looking at this example, so isn't it also the case that if you don't have a Condorcet winner, then no alternative can get more probability than 1/2 because of your definition?
So in this example, yes.
But I mean, in any example, if there's no Condorcet winner, so no alternative can get probability more than 1/2, right?
You might be right, but I have to look a little bit more carefully to it. Yeah.
All right. Let's go to the question by Florian. He asks whether the set of stable lotteries are usually small in some sense. Can you say something about that?
So it's a fixed point argument, and usually fixed points, the number of things that is fixed point is small, right? So in measure wise, in the standard notions, right? I don't have a formal theorem for it, but usually the literature on like how many fixed point there is in a fixed point mapping, that is very small, right?
So that this is some generic result, right? I mean, generically, it is probably unique or something even, right? I mean,
correct.
Depending on the precise sense of generic here. Okay.
Yeah.
Okay. So Florian, is this satisfactory answer?
Maybe just a quick follow-up. So, so you're saying the set of fixed points is small. Could it be that there are some stable lotteries that are not fixed points?
There, oh yeah, there could be. Yeah, there could be.
Thanks.
All right. I think that's if there are no more questions, then this would be the perfect point to go to the break. So we'll have 10 minutes break and we reconvene at a quarter to 4, right? Yeah. Okay. See you in 10 minutes. We can continue with the next excellent talk by Andrei Constantinescu, and he will from ETH Zurich, and he will talk about Byzantine game theory. And the next one I don't pronounce. Please explain, Andrei, what your Byzantine game theory is.
Yes. So let's first make sure I'm sharing the right screen. So first of all, thanks everyone for inviting me. Thanks Clemens for sharing. Thanks Dominic for writing me, and everyone else on the committee. Yes, this has a title, Byzantine theory, Sun Tzu's boxes, like mixing a bit of cultures in here. Like you may wonder what the hell is up with this title. Would you name a paper like this? So first of all, this is a bit of I would say position paper. Most of my works, like, I think it's the one that will spark the most interesting discussion. So that's why I chose to. So let me try to like a bit the title and try to cool in the process. So what is Byzantine? So the ones from that is maybe perhaps considered archaic work by now, but actually quite seminal. There is this very old paper by Lamport, Shostak, and Pease. And some of you may have heard about this if you are into distributed systems, consensus, blockchain, God knows what else. And I want to maybe take a few seconds to quickly read together, because it will be about, paper will also be about, but from a different angle, let's say. So that we have a group of generals of the Byzantine army, and they communicate with each other via messenger, which you can think as, some kind of authenticated channel. Maybe not even authenticated, but it's like pairwise channels between the generals. And the goal is that they should agree on a common battle plan. Okay, but the problem is that some generals are actually traitors, and they will try to confuse and deceive the others into attacking at the wrong time, attacking the wrong target, or God knows what. So the problem is to find an algorithm to ensure that generals, of course, the non-loyal ones can do whatever they want. The point is that the good ones know what they are supposed to do. And at least in this paper, they show that the problem is solvable if you have 2/3 of the honest, or actually strictly more. And distributed computing literature, people have noticed that there's always kind of this 2/3. Sometimes it's 1/3. Sometimes you need everyone to be honest if you make assumptions that are too strong. This is beyond the talk. I can talk more about it if people are interested. But one thing I want to link this with is actually Lamport et al. To phrase the problem. They said that some generals are malicious, they like to deceive, they like to confuse, right? And this sounds very much like a game theoretic issue more than a, distributed computing issue at first. So in fact, if you try to think what are the origins of game theory, of course, you may say von Neumann and Morgenstern, you may say many things. However, you go very, very far into the past and forget about this quantitative approaches defining things properly and formally. You can try to think of these philosophers and maybe Sun Tzu's Art of War, and what were they one thing that Sun Tzu was saying is that all fair poor. All warfare is based on deception, which again hints at this like Byzantine. Byzantine is generally used as a synonym for some people deceive, some people don't follow protocols, and so the token in this field generally. And he was talking about other things. He was also talking about zero-sum games, again qualitatively, and other. I can maybe like quickly show you what Byzantine agreement is formally defined, although this is not strictly necessary, but now I have 20 minutes instead of 10, as I quickly show you. It's also sometimes called consensus. You have n parties, they communicate through channels, they have inputs, and they want to give outputs. And a number t, at most t, you know that at most t are Byzantine. You know this t, maybe it's a third, it's a fixed threshold. You don't know how many are actually Byzantine, but you know this threshold t. So maybe people like this one. The other ones we call honest. It's just like terminology, but you can also say they are honest, but it's more like the terminology. We define honest to be non-malicious. And at least in the consensus problem, the goal is reach agreement on the same y, like this. And also y needs to be in some sense meaningful, because otherwise you just output 5 all the time. It's not very useful. The talk to explain what meaningful means, plus it has 100 definitions. But now my question and where this paper comes from is, but this like setup with t being bad and n minus t being good, and the bad ones just try to mess up any guarantee you can get. Like this sounds much more general. Like we can try to apply this to so many other settings. It sounds super game theoretic. We can apply it to COMSOC, apply it to like voting manipulation, apply it to so many other things. So this is the motivation, and this is something much bigger. And this is why I'm saying it's more of a position paper. But here is a puzzle, and it's actually what we solve in the paper. But I think it's quite a nice puzzle. So imagine you are at a game show, and this guy here presents you with 4 boxes. Each one has a certain amount of money written on top. That is supposedly how much money is inside. And the host tells you the rules of the game. And the rules of the game are that you have to open one box and you get the money inside. Pretty simple, right? Which box do you choose? Well, you know, you play the game, you say, okay, I choose 8. Why not? Why would I not choose 8? You choose it, the host opens the box, on $8. Of course, if this game is played multiple times, it's a bit boring for the audience. So then people organizing the show decide, let's spice it up a little. Now in the second round or the second night, if you want, you are invited multiple times to this show. You are given the same choice and you say, okay, 8 again. But now there's a catch. And the host reveals that one box will be lying, one box will be empty. Okay, I need to be a bit smarter. I cannot just choose the largest one. Well, now let's say you are invited a third time and now you think you are smart. You say, okay, let's pick 7 because of course they will try to nullify the 8 because it's the largest one. Yeah, but the host also plays a bit dirty. Maybe they take publicity just before they reveal the boxes, and based on your choice, they close that one. Sorry, they empty that box. So this is a bit of an unfair game. Actually, if I look at this formulation of the game, there is not much you can do with it. But let's think a bit more generally, like about this game. Like we can reformulate the game very slightly and say the host no longer plays dirty. One box is still lying, but instead you are interested in the word, like what's the best worst case guarantee you can get. So like you want a solution that is robust, you know, you are very risk averse, you want to pick the box the most sense in the worst case, kind of. And of course, the answer will still be that with deterministic strategies, you can do nothing. So I didn't do anything. I mean, I formulated the problem as a robust optimization problem, but I didn't do anything. But with this formulation, I can more easily say, what about randomized strategies? And it turns out this is actually a randomization against an oblivious adversary. Like it's the standard definition, but I find it a bit easier to motivate this way. And this idea of like robustly optimizing is also very well funded in itself, like more than the game. The game is a nice puzzle, but this is more useful. So now my question would be, with randomization, like what can you try to do? Of course, again, you cannot get worst case guarantees, but you can try to get something better in expectation. So maybe if you say, okay, let's do 50-50 between the largest 2 boxes. And now I will do this example relatively slowly to really illustrate what can happen. And how the problem is really defined, because again, you have maximization, expectation, all of this at the same time, it may be a bit confusing. So let's go slowly through it. So in expectation, if you do 50-50, two options. Again, you are very risk averse. In scenario one, it could be that is empty, and then you get an expectation of 50% of the second one, which is 3.5. Now, there is a second scenario where, of course, you get 50% of the first box because the second one is empty. There's also scenarios where both of the top two boxes are like okay, and the empty one even doesn't exist, or it's maybe one of the last two, in which case you get 7.5. But we don't care about this case. The worst case is the 3.5. And now you may say, like, if you're a game theorist or generally a COMSOC person, you may argue, okay, but we know the Nash principle of indifference. When we see two things like this, let's try to make the two expectations equal. And the answer is yes, you can do a bit better, change up the probabilities a little. You can decrease a bit the first one, increase a bit the second one, do the same analysis, you get a bit better, which by a tiny bit. Now you may argue, but okay, but why use only two boxes? We can try to use all four boxes and try again to equate the probabilities, like in the Nash indifference sense. Well, if you do that, it's again a bit better. So 4.18, and before it was 3.73. Now, the surprising fact is that it turns out that even though you have 8, 7, 5, 4, you know, the difference between the first two is 1, and the difference between the last two is also 1, and the difference in the middle is 2, so it's a bit larger. You would expect that you either take the first two or all four. You may never want to take 3 of them, but the answer is the best you can do is if you take only 3 of them and equate the probabilities, and you get something a bit better. And probably this is the best for this instance. So this is to show you a bit that this is a bit less obvious than it sounds, how to solve. You have this adversary that nullifies a few boxes, actually one box, and it's no longer so obvious how to reason about what is larger than what. So yeah, can we better? No. Can we do better? No, for this example. So now, more generally, how much time do I have left? I want to plan a bit.
Well, you have at least 10 minutes. I would say you have.
Okay, that's more than enough. Okay, thank you.
Yeah.
So now the general setup of the paper, just to reiterate over what I already said, but more generally, the setup is you have n boxes. Each one has an advertised value, monetary value or utility value if you want. It doesn't quite matter if you assume they are equal. Some of them may be lying, but we get to that later. I assume they are sorted in non-increasing order, because why not? It makes just reasoning slightly simpler, but it's the same thing. You will open one box, you get the money inside. Your output, because again, we are in the randomized oblivious adversary setting, will be a distribution. So some numbers, P1 up to Pn, that sum up to 1, and they are between 0 and 1. So from this example, the box we open, this is what you are supposed to output. The expectation you get, at least so far, because I didn't specify any box being empty, will be this one. But because actually one box may be empty or lying, which is kind of the same thing, because I'm assuming worst case, I'm assuming the adversary cannot go negative on the amounts, that would make the problem a bit ill-defined. Because of that, you actually get the sum, but for all positions except position B of the empty box. And of course, your goal is, so the goal of the adversary is to minimize this. They will choose the box that is, you know, the one that messes you up the most. And your goal is to maximize that. So this is really a maximin in the over a distribution, so randomized maximin. And it turns out like this is really the maximin solution concept for a zero-sum game, same as Stackelberg, same as Nash, same as everything else, but you don't need to really think of these notions to analyze the game. In some sense, they even make analyzing it more complicated when you get to the later parts of the paper, but you can think like that, and they are that notion. So now the theorem, the general theorem you can prove for this setting, one box you open, one box is empty, you don't know which, you want to maximize this. What you get is that the optimum is always you pick a prefix of boxes for each you make the expectations equal, and there is a suffix of boxes where you put nothing. This is probably something you can get directly from Nash, at least if I write it this simply. But you can generalize a bit. You can say that maybe T boxes are lying, and then it becomes slightly more annoying to just go Nash. like you probably still can, but it's a bit more annoying to prove. It's more easy to do elementary stuff. So even if you consider T boxes being empty, and now on the slide, I just reformulated everything with T, but it's exactly the same thing. We open one, the adversary messes up T boxes. Here, it's still optimal to pick a prefix, equate the expectations there, and for the suffix, you put 0. And this also means that with a tiny bit of work, you can do linear time. You can compute everything super fast, like because it turns out that to equate those expectations, you just set the p's inversely proportional to the v's. It's some very simple equations, and you get linear time computability. To prove that this is actually true, most of it is just exchange arguments. Assume, like, think what happens when you increase a p, decrease another p, both by epsilon, things like that. I can make most of the proof work like that, but really I get something slightly weaker if I just do that. I could not quite finish it in this like nice form of the theorem. I can still get linear time just with exchange arguments, but it's a bit more cumbersome. But to actually get that you set them all equal and the prefix is all zeros, I play a bit with writing this as an LP and taking the dual and noticing some stuff about the dual. If somebody has a fully combinatorial proof, I would love to see it. But so far, I can only prove that it's a prefix plus one value that could be 0 or not, and the rest 0. But to get that the suffix is all 0, this I could not get directly, and maybe somebody else can. Now, this is all nice and dandy, but you may ask immediately, okay, you have T boxes that are empty, but and one box that you open. However, what if you have L boxes that you open and T that are lying? Okay, very natural question. Yeah, let's try to study this in general. In fact, if you think for a second, this is really the multi-attacker, multi-defender, some zero-sum variant of a Stackelberg security game. So it is really that, but a zero-sum variant, but it is that, if some people are starting to make connections here and there. So if you want to do it with L boxes that you open, you of course need to change a lot of other things on the slide. One of them is the distribution is no longer over values, like over numbers, it's over size L subsets. So it's a bit harder to describe combinatorially what the distribution is because it's a quite highly dimensional object. Of course, the thing we are maximizing is no longer this nice sum, but the last term needs to be the chance I is in the set, which is now just that, which before was just pi, so it was a bit nicer. Now it's that. But you can still say that this is pi prime, let's say. And if this is pi prime, this is really the marginal of p across every possible axis. So if you try to think like that, it's actually really helpful because these pi primes have to be between 0 and 1 because they are still probabilities, and they have to sum up to L if you just exchange the order of summation and think of the fact that you always sample exactly L, so they do sum up to L. So now you may ask, can we just, find the optimal p prime directly, like just constrain it to 0, 1 and to sum up to L and say, find the optimal p prime and that's it? Well, it's not obvious that the answer is yes, because maybe there are some p primes like this that satisfy the note part, like the part over here. Maybe there are some p primes that do that, but maybe they do not satisfy, but maybe they cannot actually come from the marginals of a full distribution p. And it turns out this is actually quite well known that it's always possible to make such a distribution p. Like here is a nice thing you can use. You can use it in so many other things. Like this is like just a lemma you can use in fair division. You can use in participatory budgeting. You can use anywhere else. We were not the first to notice this. Like if you have some p primes, like the marginals, that 1 and sum up to L, then they can be implemented with a distribution. So again, these are marginals of a distribution over subsets of size L. If the marginals are, not too weird, they can always come from an actual distribution. And this is very useful. And it turns out you can explicitly compute such a distribution in n² time, which means it also has very low support, has like linear support, and it's n entries per element in the support. So it's kind of optimal. You can compute it like that. You can see the reference in the paper. We just cite a paper in fair division that does that. You can actually, if you don't want the distribution explicitly, you can actually sample from such a distribution in linear time. And this is just application of the standard dependent rounding paper. You don't even need the dependent part. You just need randomized rounding and the fact that it works. So with all of that, it turns out, yes, it does suffice to try to find the optimal p primes that are between 0 and 1 and sum up to L. And now this makes the problem much nicer. Now you can actually try to solve it again with exchange arguments. And it turns out you will be able to do it in linear time. So the proof idea, how much time do I have to see how much I can spend later?
Now around 2 minutes, let's say.
Then let's make this quicker. So the proof idea will be a water filling argument. Let me show you a bit like this. You will make rectangles that are VI high and 1 over VI wide, such that the area is 1, because the area will correspond to units of water, like this, or units of probability mass in P prime. And height, because I set the VIs to be the heights, they will represent units of expectation. And what you will end up caring about is you can prove the distribution always looks something like this. You always have like this line E that is like, this like an upper bound of expectation. And based on this E, you always from left to right kind of try to saturate the distribution. You will have some entries where it raises up to the maximum E, and then a few boxes where it just fills the box, and one box that may be empty. Actually, not empty, it may be not completely full. And the idea will be that you can just move water continuously from left to right, like decrease E and see where the water goes. This will be a piecewise linear function. You can try to online find its breakpoints, and in linear time, you can find what's the best thing to do. Okay, this we can discuss more. It's not so relevant. My actual, position on this, and this is what I really want to discuss more with you guys. I have a recipe for like a whole research direction which we should try to do more in COMSOC and AGT, like any problem we care about. But what happens if you have malicious players that just try to destructively interfere? So really destructive interference with the outcome, like T malicious players whose sole goal is to make the outcome possible. Why should you do that? Because this is really about robust solutions. Like what happens when you have people who really just want to mess up your system. It also connects with all of these things that people have done in distributed computing. And it's a bit weird that, we have all of these people who looked at this threshold T all the time in distributed computing, but we don't look so much at this definition in COMSOC and in AGT. And I think we should do that more. And generally, it's quite underexplored. There are some papers on it, and I can tell you a few examples. Like we do have a paper at PODCI to be presented by a co-author of mine in like a few weeks on Byzantine stable matching. So that's cool. But there's lots of things that have not quite been done. I know I have been told that some have been attempted or done to some extent, but here is how I wrote it before being told all of that. Like, what about fair division, where, maybe T of the items or T of the players are, malicious? What about voting, when you have people who want to throw off your outcome? What about mechanism design? I know there is at least one work in hedonic games that did something like this. I know there is also a paper in task assignment that does something quite similar to our problem, and so on. So maybe that's all I wanted to show you. And yeah, I open the floor to questions, and I would really like all your feedback and other examples of papers that do anything like this.
All right, so thank you very much and nice talk.
Thank you.
Yes, and let's open the discussion. So who wants to ask questions? Nizark.
Hey, it's great talk. So can you explain a little bit what kind of Byzantine fair division notion you had in mind?
Yeah, that's tricky because I didn't think so much about it, but let me quickly think which one it would be. So like, what can you actually do? Like, for instance, you can, so to be honest, all of this links a lot with manipulation problems and more like even with strategy proofness problems, but it's not exactly the strategy proofness problem, but you can think of it this way. You have, let's say, some indivisible items and some agents that have, maybe additive preferences over the items. And let's say each person, when you talk about strategy proofness, what you care about is that, it's truthful to just reveal your actual preferences. Okay, but that's more about nobody can improve their allocation by misreporting. Here, I care about something else. I care, can a coalition of players misreport and make what others get worse? Like, this would be the idea. Like, I'm not sure what notion you would want to pick, but I'm sure you can
probably
look at
some kind
maybe
of
efficiency. What?
Yeah, probably some kind of welfare approximation, because for envy freeness, I mean, as long as like the others are reporting their own honest values, the allocation would be envy free up to 1 for them. So it's kind
Yes,
of
it
like
will. It
regardless of
will,
what
but it
everybody
may
else
be
reports.
less. But it may
But
be
yeah,
less
so yeah,
efficient. That's for sure.
right. Yeah, we could look at some welfare approximation.
Yeah, you can look at welfare approximation. For efficiency, it makes perfect sense for every kind of efficiency. I'm sure there should be also a way to look at envy freeness, because I don't know, it sounds to me similar to the Byzantine stable matching thing we have, but I need to think a bit more to not say something stupid. But yeah, you can probably look at so many things.
Sounds good.
But perhaps as a general remark, I mean, if you look at people who want to hurt others, right?
Yes.
Then you're simply talking about people who have non-self-centered preferences, right? They don't only care about what happens to them, but also what happens to others. I mean, this is, of course, I mean, this is behavioral economics, and there are many papers and approaches to that. But you have to be careful in making precise the question that you have. I mean, if you want to welfare maximize with people who want to hurt others, right? Then you have to first think about what does welfare maximization mean here?
Yes.
Or do you want to exclude those people from your fairness, welfare, or whatever considerations? So I think it's a very interesting program, but there are many ways to go, and one has to be very careful. What kind of problems do you address, and what don't you want to address here?
Yes. It's a really difficult thing to, like, to be honest, the more I look at this paper and this idea, you find more connections with more fields. And that's why I would be very happy to collaborate and talk much more with everyone about this, because it's really, here you need the experience of everyone to tell what has been done and what connects with what, and have this like unified position on what's new and what's not. But I totally agree. It's really tricky in exactly what you want.
Yeah. Peter, you have a question.
Yes, thank you for your interesting talk. I'm curious to what extent you are looking for solutions within a restrained model, because in the Byzantine general problem, in principle, the defectors can do everything. They may attack the other generals, which is completely outside the problem as you are formulating it. And for example, if I'm thinking about fair division, then one thing what a defector might do is simply enter the game show and steal the object.
Yes.
And things like that. So in that sense, it seems that your problem is very underspecified.
Yes. So I think I can already make a comment which may help you give you a follow-up and to see if that's what you actually want to get at. So the idea is that one thing, and this is also like a common complaint I have in the literature at the moment, like if you look at the Byzantine X, where X is anything, agreement, consensus, whatever you want, literature, or if you look at these papers that do consider some sort of social choice plus Byzantine, which there's not so many of, and usually they go under a different name, like, the split is usually as follows. In Byzantine generals and Byzantine agreement, it's a distributed problem where everyone inputs their own, input, and they run this complicated distributed protocol where people, exchange messages, and maybe the protocol says, can my mouse be seen actually? My mouse, does my mouse?
No, mouse is not seen actually. No.
No. Work. It doesn't matter. So if let's say x1 in the picture here wants to send the value to x2 and to x3, or maybe even better, let's say x3, who is the bad guy, is supposed to send their value to everyone, but because he's bad, he will send something to x1 and something to x2, right? So they can do this kind of attacks where people get inconsistent views. And this is like an intrinsically distributed problem. Now, in the problem I've specified, there is sort of a central planner, right? Like there is somebody who gets the preferences and tries to solve the problem and gives everyone what is supposedly their part, you know, like what they are supposed to do. And now there is actually there's a simple way to link this. Like the distributed systems field gives us a lot of tools to simulate protocols with a central planner in the setting without a central planner. And these are usually protocols for reliable broadcast, protocols for core set agreement, protocols for all of these consensus things. So in principle, you can always decouple the problem into two parts. A part where you solve the distributed aspect of it, which is usually kind of solved already by the distributed agreement literature, and a part where you want to solve the social choice aspect, which is the aggregation that the centralized planner has to do. And usually in the distributed systems field, this aggregation is very simple. But for social choice problems, this is the actual, you know, nail in the coffin, kind of.
Okay, there is one other remark I like to make, that I'm not sure whether you're aware that there is an rather restricted literature on the topic, to what extent Sun Tzu actually has concepts in game theory implicit in his work. If you're interested, I can provide you more information.
Sure. Honestly, I am not like a philosopher. To some extent, this was my supervisor's idea. This was Roger's idea, because he's much more, you know, he's better read into all of this like tech.
It just
So I will
so
not be able
happens
to
that
comment.
I recently completed a book with some co-authors, including my wife, where this is a chapter where it's explicitly discussed what's known in the literature.
Yes.
All right. So that should be a perfect then discussion between you and Peter.
Yes.
You should get into contact with Andrei on this. But we have to stop here, I am afraid. Let me just announce that the next edition of COMSOC video seminar will be on the 25th of June. Dominic, do you agree? 25th of June?
I agree.
Okay, very good. Do we already have speakers? I don't know. Dominic, you must help me here.
Yes, we will hear from Sanjukta Roy and from Rupert Freeman.
Wonderful. So thank you for the speakers, for the excellent talks. Thanks for the audience, for the attendance, and see you in around 1 month in June again. Bye, everyone. Bye-bye.
Bye.
Bye-bye.
Bye-bye.